Welcome back to Calculus 2. I'm Dr. Jeff Groh. Today we're going to talk about the comparison tests. Make special note of the plural form here. That's because we are going to talk about two different kinds of comparison tests. First, we'll talk about the direct comparison test, which is very straightforward to prove, a little more difficult to actually implement. Then we'll talk about the limit comparison test. The proof of the limit comparison test will use the direct comparison test. But the limit comparison test is a lot easier to implement usually. To motivate these comparison tests, let me show you some examples. Suppose I have the sum, as k goes from 1 to infinity, of k cubed plus 1. If only that plus 1 were not there, this would be a p-series with p equals 3, which is greater than 1, and therefore it would converge. Does the 1 really matter? When k gets really big, like 1,000, what is 1,000 cubed? 1,000 cubed is 1 billion. A billion and 1, does the plus 1 really matter? Especially when you're talking about 1 over a billion? That's a very tiny number. You can see that when k gets big, the plus 1 doesn't make any difference. It's as though you could ignore it. You would like to ignore it. You need to ignore it. There has to be a theorem that allows you to ignore that plus 1. And we are going to have two theorems that will allow you to do that. The first one is called the direct comparison test, and the second one the limit comparison test. We'll begin with the direct comparison test. It goes like this. Suppose 0 is greater than an, and that's less than or equal to bn for all n that are elements of the set of natural numbers. Now here's the idea. If the sum of the larger series converges, if the sum of the larger series converges, then the smaller series must converge too. Alternatively, if the smaller series diverges to infinity, then the larger series must diverge as well. The proof goes in kind of an obvious way. We'll form the partial sums and then we'll look at what happens with these limits. If the limit as n goes to infinity of the sum as k goes from 1 to n of bk is finite, in other words, if the larger series converges, then the partial sums on the smaller series form a monotone increasing sequence that is bounded. by the Strass Theorem, the limit as n goes to infinity of the sum as k goes from 1 to n of a sub k must converge. It's a bounded monotone sequence. Also, if the limit as n goes to infinity of the partial sum of the smaller series diverges to plus infinity, then the limit as n goes to infinity of the nth partial sum on the larger series must also diverge to plus infinity. And that's the end of the proof. So for example, if we have the sum as k goes from 1 to infinity of 1 over 2 to the power of k plus 1, you would like to say that when k gets big, this exponentially growing function in the denominator is going to completely dominate the denominator. The plus 1 shouldn't matter. You should be able to ignore it. Why not? You have to make sure that you get the inequality going in the right way. This will behave very much like a geometric series when k gets big. We just have to make the comparison in the right direction. So we'll use the comparison test. That's a short way of saying the direct comparison test. Sometimes we just call it the comparison test. And we'll note that if we make a denominator bigger, that makes the fraction smaller. So since this series is a geometric series with common ratio equal to 1/2, that has a magnitude less than 1, that series converges. Since the larger series converges, that means the smaller series converges too. What if I have the sum as k goes from 1 to infinity of 1 over 2 to the k minus 1? It's a little more delicate this time, and the reason is 1 over 2 to the k minus 1 will be bigger than 1 over 2 to the k. The convergence of this series doesn't tell you anything about convergence or divergence of the larger series. You need the inequality to go the other way. Fortunately, there is a nice little trick that you can learn for handling this situation. We want to prove that this series converges because we believe in our heart that it behaves like a geometric series with a common ratio equal to 1/2. Especially as k gets big, it behaves more and more like that. So we want to find something bigger. How do we find something bigger? Well, you need to make the denominator smaller. Subtracting 1 makes it smaller, but we need to make it smaller still in a strategic way that converts this series into something bigger that we can prove converges. So here's the trick. I'll have this 2 to the k. How about 1/2? 2 to the k. We'll subtract more and more, and that will make the denominator smaller and smaller, which makes the fraction bigger and bigger. But hopefully not so big that it fails to converge. We need this thing to converge to a finite result. We can simplify this by factoring the 2 to the power of k out in the denominator. We'll have 1 minus 1/2. This 1 minus 1/2 is 1/2. And so we'll have 1 over 2 to the power k minus 1. So we will in fact be able to use the direct comparison test to a geometric series of the form 1 over 2 to the power k minus 1. Now that we know that the test will work, we'll declare what test we're using. And again, the use of the word direct here is kind of optional. We'll compare it to the sum as k goes from 1 to infinity of 1 over 2 to the power k minus 1, which we know is bigger than or equal to this one. This is a geometric series with common ratio equal to 1/2 that has a magnitude less than 1, and therefore it converges. Since the larger series converges, the smaller series converges too. I want you to include the derivation of that inequality on the previous page. We can also apply the comparison test to prove divergence. Suppose we have 1 over the square root of k, say, plus 1. We need to find a series that is smaller that diverges. Does this series converge or diverge? If you ignore the small stuff, the plus 1, it looks like a p-series with p equals 1/2. Since 1/2 is less than or equal to 1, you suspect that maybe this series will diverge. It should probably diverge. We need to use something smaller that we can prove diverges. So we need to find something smaller. How do you get a fraction to be smaller? You need to make the denominator even bigger. So there's a trick to this one too. Try this. We'll have the square root of k plus about 1/2 the square root of k. As long as k is bigger than 2, this should be fine. As long as k is bigger than 4, this should be fine. Note, convergence and divergence doesn't care about the first few terms in the sum. It only cares about convergence and divergence doesn't depend upon what happens with the first few terms in a sum. It only depends upon what happens in the tail, way out in the tail of the series. So if this happens, if this inequality is true for k bigger than or equal to 4, then it's good enough for our purposes. So notice on the right-hand side here, this is 1 over 3/2 root k, which we can call 2/3 of 1 over root k. When we put this inside of a series with a sigma here, the 2/3 can be factored out, and it will be literally a p-series with p equals 1/2. We'll now declare the test that we're going to use. We're going to use the comparison test to the sum as k goes from 1 to infinity of 2/3 1 over k to the 1/2. That is a p-series, so we use the p-series test. P equals 1/2, which is less than or equal to 1, which means that the p-series diverges. Since that was smaller than the series that we started with, the original series diverges as well. Note, whenever you use the comparison test, you always end up using some other test as well. With the direct comparison test, you have the added complication of trying to figure out which direction to make the inequality go, and how to construct a series that you can prove either converges or diverges. I don't know about you, but I'm a little too lazy for all of that normally. I need a test that is easier to implement. I want a better test. I want the limit comparison test. For the limit comparison test, we suppose that an and bn are positive, and the limit as k goes to infinity of a sub k over b sub k is an element of the positive real numbers. That means it's not zero, doesn't go to infinity, it goes to some finite real number. Then, both series converge or both diverge. You can think of it this way. If this limit ends up being some positive real number, then these series go to zero at a rate that is off by just some factor, whatever the factor is, whatever the value of the limit is. So the two series will go to zero at essentially a proportional rate. That means both converge or both diverge. Now let's prove this. Suppose L is the value of that limit. What does that mean? Given an epsilon greater than 0, there exists some natural number n such that if n is bigger than or equal to big N, then the absolute value of a sub n over b sub n minus L will be smaller than the epsilon that you chose. This gives us negative epsilon is less than an over bn minus L is less than epsilon. If we add L to all three parts, L minus epsilon is less than an over bn is less than L plus epsilon. We'll multiply each part by bn. We'll have L minus epsilon times bn is less than an is less than L plus epsilon times bn. Let's choose epsilon so that L minus epsilon is still positive. We'll choose epsilon to be so small that this is still positive. We know that L is positive. We'll just be sure that epsilon is so small that L minus epsilon is positive. By the comparison test, it follows then that if the larger series converges, then the smaller series converges. The L minus epsilon won't affect convergence, that's just some constant. The fact that we're adding these only from some n in the tail won't affect anything either, because the first finite number of terms doesn't affect convergence. E inequality only holds in the tail, so the direct comparison test only applies in the tail, but if you get convergence in the tail, then the rest of it will converge too. Also, if the larger series L plus epsilon times, as let's see, k goes from n to infinity of b sub k converges then the smaller series, the sum k goes from n to infinity of a sub k, also converges. We can also use that triple inequality to show that if the smaller series diverges, then the larger series also diverges, and that will complete the proof. So I'll just write dot, 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 and then double hash mark, and the proof is over. Let me give you an example to show you how this works. Suppose I have the sum as k goes from 1 to infinity of 1 over 5k minus 2. Converge or diverge? Remember, we can ignore the small stuff. As k gets big, the minus 2 becomes meaningless. Just ignore it. But what about the 5? If you've ignored the 2, can't the 5 come out as a factor of 1/5? And then, aren't we just looking at the sum of 1 over k? Isn't that the harmonic series? I suspect that this diverges. It diverges in the same way that the harmonic series diverges. The easy way to prove this is to use the limit comparison test. We're going to compare it to the harmonic series. What you have to do is you have to calculate the limit as k goes to infinity of the ratio of these terms, 1 over 5k minus 2 divided by 1 over k. 1 over k will flip, and we'll end up with a k here. As you can see, we get a polynomial over a polynomial, both of degree 1. You take the ratio of the leading coefficients when you calculate the limit. So the limit is 1/5, which is an element of the positive real numbers. Both converge or both diverge. But the harmonic series diverges, so our series diverges as well. Let's do another example. Suppose I have the sum as k goes from 1 to infinity of the square root of k over k squared plus 1. Converge or diverge? What does this series behave like when k gets big? To answer these questions, note that if k gets big, we can ignore the plus 1. The square root of k is k to the 1/2. K to the 1/2 divided by k squared, that's 1 over k to the power of 3/2, 2 minus 1/2. This looks like a p series with p equal to 3/2. That's bigger than 1. This converges. We just need to prove it. So we will use the limit comparison test to the sum as k goes from 1 to infinity of 1 over k to the 3/2, where p is 3/2, strictly greater than 1, which therefore converges. Now we will implement the limit comparison test. We'll take the original series, the square root of k, over k squared plus 1, and multiply by the reciprocal. When you divide a fraction, you invert and multiply. The square root of k times k to the 3/2 is k squared. So in the limit, we get 1. That is a positive real number. Both converge or both diverge. Since the p series converges, our series must also converge. Let's look at, in the next example, the sum. As k goes from 1 to infinity of the sine of 1 over k. We have a sine function. Isn't this going to get complicated? You need to remember, in the limit as x goes to 0, sine x over x is 1, which you may easily prove using L'Hopital's rule if you don't remember. That means as the argument of the sine function gets tiny, and as k gets big, 1 over k will get tiny, sine x and x will be very close to each other. That means the sine of 1 over k and 1 over k are going to be pretty close to each other as k gets really, really big. You might deduce that this series behaves like the harmonic series when k gets big, and therefore it diverges. Let's prove this. We will, of course, use the limit comparison test to the harmonic series, which diverges. To prove that these diverge in the same way, we'll take the limit of the ratio sine of 1 over k divided by 1 over k. Now, there are a lot of ways of evaluating this limit. One way is to replace 1 over k by x. As k goes to infinity, x will go to 0, and the limit is 1. Another way would be to just use the L'Hopital's rule. Either way, you get a positive real number. So, both converge or both diverge. Since the harmonic series diverges, the original series must also diverge. Sometimes there's more than one test that you know how to use on a particular series. Let's look at the sum as k goes from 1 to infinity of k over k squared plus 1 quantity squared. Now you may use the integral test to prove that this series converges, or you can try the limit comparison test as well. Notice that if k is big, then the plus 1 doesn't matter. The denominator will look like k to the power 4. Canceling the k in the numerator, this looks like 1 over k cubed. It looks like a p-series with p equals 3. Since 3 is bigger than 1, it will converge. Let's use the limit comparison test, since that's our new toy. To the p-series, the sum as k goes from 1 to infinity, 1 over k cubed. This is a p-series. P equals 3 greater than 1, therefore converges. To implement the limit comparison test, we'll have k over k squared plus 1 quantity squared, and we'll multiply by the reciprocal, k cubed over 1. The numerator ends up being a polynomial of degree 4 with leading coefficient 1. The denominator also looks like a polynomial of degree 4 after you FOIL it out, with leading coefficient 1. Therefore, taking the ratio of leading coefficients, the limit is 1, which is a positive real number. Both converge or both diverge. Since the p-series converges, this series converges too. Let's try one more example. Let's suppose we have the sum as k goes from 1 to infinity. Let's try something like 3k minus 1 over k squared plus 2k plus 10. As k gets really, really big, these lower degree terms don't really matter. Notice that if k is, say, 1,000,000, which is a pretty big natural number, 1,000,000 squared What's a million squared? A million squared is 1 trillion. Plus 2 million. Who cares about 2 million if I have a trillion over here? If you have $1 trillion and $2 million drops out of your pocket, do you care? Not really. You can have $1 million drop out of your pocket for the next 1 million days and still not run out of money, and you aren't going to live another 1 million days. So it won't affect you at all. So as k gets big, these other lower degree terms don't matter. The only thing that matters are the highest degree terms in both numerator and denominator. So this series is going to look like 3k over k squared. The 3 doesn't really matter because it could be factored out at that point. It's going to look like k over k squared, which is 1 over k. That's the harmonic series. This thing is going to diverge. The easy way to tell that is to use the limit to comparison test to the harmonic series. Which is the harmonic series, and diverges because everyone knows the harmonic series diverges. It's famous. So we'll take the limit as k goes to infinity of 3k minus 1 over k squared plus 2k plus 10, and we'll multiply that by the reciprocal. We now have a quadratic over a quadratic. The limit is 3, which is a positive real number. Therefore, both converge or both diverge. Since the harmonic series diverges, this series diverges as well. I'd like to do one more example. Suppose we have sequences having positive terms, and these series both converge. Show that the series that you get by multiplying these terms also converges. The proof goes like this. Since the series, the sum as k goes from 1 to infinity of a sub k converges by the divergence test, if it does converge, then the terms must go to 0. You get the limit as k goes to infinity of a sub k is 0. Thus, given epsilon greater than 0, there exists some natural number n such that if you go far enough out, then the distance between an and the limiting value of 0 will be smaller than epsilon. It follows then that an bn will be less than or equal to, well, an is smaller than epsilon, and bigger than or equal to, how about minus epsilon? We can now use the direct comparison test. The larger series converges, at least for n values in the tail, and hence converges generally. So the smaller series must also converge.